The ingredients have been so far. So we have introduced this quantity of charge. We could call it topological charge. And for this particular theory, we're only allowing a charge of 0 and 1. 0 is the charge of the vacuum. 1 is the charge of a single one of these Fibonacci anyons. But even if we have many of these Fibonacci anyons, the only allowed possible total charges are 0 and 1. That's all we're allowing. There are the fusion rules, which we had to introduce when we considered the case of two particles. And there's only one non-trivial fusion rule, which I can write like this. It tells me if I combine two charge 1 objects, the total charge can be either 0 or 1. And then there are the trivial fusion rules involving fusing. If I fuse anything with the charge of the vacuum with something else, it just won't change the topological charge of that something else. And then, so this was, when we introduced one particle, we had to introduce charge. When we introduced two particles, we had to introduce fusion rules. When we introduced three particles, we had to introduce something else. This is the F matrix. And this, I think it's going to be useful to have this on the board. So let me write this. In fact, let me write it out explicitly like so. So here are three anyons with charge 1. If the charge of the two leftmost is 0, I can write this. I'll write it out explicitly like so. It's a sum. This is just a basis change from one basis where I combine the two particles on the left to another basis where I combine the two particles on the right. 0, 1, 1, 1. And likewise, if this is 1, and the total charge is 1, then we have F 1, 0, 0, 1, plus F 1, 1, 1, 1. And let me also add, just down here, if the charge of all three is 0, if the charge of all three is 0, then if these two must have charge 1, because if they didn't have charge 1, then when I combine it with this Fibonacci anyon, the charge would be 1. And in this case, the F matrix is trivial. It's just 1, the F matrix element. These are just two. These are just the same state. And another point that will be useful is it's really these two cases here are the only non-trivial cases where the three particles, or these don't necessarily have to be particles, they can be collections of particles with some well-defined topological charge. Only the case where all three of these things have charge 1 is non-trivial. If this was a collection of particles with charge 0, again, everything is trivial and the F matrix element is 1. So these are really the only two non-trivial cases here. Okay. So one of the things I've done is I've assigned a homework problem set. The good news is, there's no grade. But at some point you might want to do it. In fact, you could, and I actually think it's something it is actually worth spending the time to actually solve this equation for the F matrix. It's a transformative experience. And so let me, in fact, I think I want to give you some help. Just let me go through a few examples of how one can actually work out the equations that correspond to this and eventually solve for the F matrix. And so, for example, let me choose a particular labeling here, 0, 1, 0, that's consistent with the fusion rules. And if you remember what this equation tells me is I can change from this basis to this basis. Or if you like, I can imagine expanding this state in this basis and reading off the coefficient of this of this basis state. And I can perform that calculation either by going along the top of the diagram, the sequence of F matrix operations here, or I can go along the bottom part of the diagram, and I have to get the same answer. So I think it's useful to choose to label particular cases here. So any, put any consistent labeling here and any consistent labeling here, and work out what is the coefficient. If I expand this state in this basis, what's the coefficient of this term? So going along the top, so we have this application of the F matrix, or change of basis. I'm going to move this oval from here to here. So now I'm going to see, this is a test really more of whether of how successful my summary is. Can someone tell me what is the F matrix component that enters in here when I move this oval from here to here? It's 1. This is a trivial case. The easiest way to see it is that, well, the total charge here is 0. But also, the charge of these two is 0 as well. So in fact, the rule is simple. The only time we're going to get something non-trivial, something that isn't 1, is when it corresponds to something like these two cases here, where we have 3 objects with charge 1 and their total charge is 1. That's certainly not the case here. So one thing let me label. I know the total charge is going to be 0. The total charge of these two is going to stay 0. And then the total charge of the solid oval here also has to be 0 to be consistent with the fusion rules. And we know that because it doesn't correspond to either of these two cases, it's just 1. In other words, a long-winded way to say these are just two equivalent ways to represent the same state. Going from here to here, move this oval from here to here, what are we going to get? 1 again. Sorry, it's another trivial case. So the upshot of this is these two states are the same state. We learned that by going along the top part of the path. But what if we went down along the bottom part of the path? Well, so now if I move this oval from here to here, let's see, before I ask, let's fill in the total charges. We know that, again, the total charge is 0. And the total charge of these 3 particles is 1, that none of these change. So now the question is, what's the total charge here, and what is the F matrix element? So now what do we get? So now if we focus on, we're performing applying the F matrix to the Hilbert space of these 3 particles right here with total charge 1. So now we are in this case. In fact, we're right here. And that means there are 2 possibilities going from here to here. If I expand this in this basis, it's a sum of 2 states. And so I'll label that B. B can be either 0 or 1. And we're going to have to sum over both possibilities. And depending on whether B is 0 or 1, the coefficient is F0B. That's the element of the F matrix. OK? Now let's go from here to here. Again, the total charge is going to stay 0. And the charge of these 2 particles will stay B, whatever that is. It doesn't matter what B is. If B is 1 or 0, it's always going to correspond to the trivial case, in particular because the total charge is 0. None of the cases for whatever possible value B has could correspond to either of these 2 cases. So again, in this case, we should get just 1. Then finally, from here to here, for this basis change, what are we going to get? I heard it already. So FB0, because this is again a non-trivial case. Total charge is 1, so FB0. Okay, and so from this I can read off an equation. If I follow the top path, it tells me that if I expand this basis state in this basis, the coefficient of this term will be 1. If I go along the bottom, I have to sum over both possibilities for B. And I calculate the same coefficient, and I find it's this expression right here in terms of the elements of the F matrix. So we found an equation that relates the components of the F matrix. I actually think it's worth doing one more example because this is atypical. Let's go from 0, 1, 1 here to 1, 1, 1. Going along the top, this first move here, what's that going to be? again, since the total charge of these two is 0, it doesn't correspond to either of these two cases. It's really, if the total charge is 0, I can just erase them. Let me, again, label the charges here. Total charge is 1. Total charge there is 0. And then the total charge there has to be 1. But even though the total charge here is 1, because the total charge of these two is 0, again, we get 1. The rule is really just look and see, does it correspond to either of these two cases? This doesn't, so we just get 1. These are the same state. Now, let's go from here to here. So now the three objects are this Fibonacci anyon, this Fibonacci anyon, and these two which have charge 1, and the total charge is 1. So this is a non-trivial case. And to see if I'm making any sense, maybe someone can tell me what term goes here. F01, okay, brilliant. But there's still only one. I mean, we don't have to sum over paths. So sum over possible intermediate states. There's just one term here, or product of these two terms. Going down the bottom, total charge is 1 here. Again, the total charge of these three is 1, and so the total charge here can be either 0 or 1. We're again in the non-trivial case. This is F0b, same as before. Now we have to be a little bit careful here. I'm going to move this oval from here to here. And let me put in the labels, charge 1, B. And the subtlety here is, well, if B is equal to 0, then it's a trivial case because we don't have, it doesn't correspond to either of these two cases here. We don't have three objects with charge 1. It's only for the case B equals 1 that we correspond to this. And for that case, we will get an F matrix element. And so to take care of both cases, if B is equal to 0, it's trivial, so we get 1. If B is equal to 1, then the F matrix element is F11. And the reason, by the way, the reason why I know this is 1 here is because that's where I'm ending up here. So this is really the trickiest part of the whole calculation is working out these terms. Then finally, going from here to here, what's the coefficient going to be? FB1, okay. All right, so again, the top path, we just have F01. The bottom path, we have to sum over the possible values for B, and we get this expression right here. And so we get a second equation. And if you continue this, and this is what I've assigned in the homework, you should find 7 equations. So I've done 2 of them for you. Because there are 7 non-trivial cases for ways to label these states consistent with the fusion rules. It's also true that, I mean, and if I reverse the order of the arrows, I get to, it doesn't change the equations you get. So really, if you work it out, there are only 7 possibilities for assigning the charges here. And so you'll get 7 equations. And you'll have to solve them for F00, F11, F01. In fact, what you'll end up solving for is the product of F01 and F10. But then, and using the fact that the resulting matrix has to be unitary, you'll find there's essentially a unique solution. And it has this form right here. And by the way, it's worth noting that it's kind of remarkable that there's a solution at all because there are more equations than unknowns. And in fact, for different choices of fusion rules, there often are not solutions to this equation. So it's not a foregone conclusion. And furthermore, the fact that there's a unique solution is one of the things that makes these non-abelian particles ideal for quantum computing because it suggests there's some rigidity in the system. If there was a continuum of possible F matrices, if I could choose any F matrix I like, that would be a possible source of error. But in fact, it's uniquely fixed essentially by the fusion rules. There's an irrelevant phase which you can multiply these two elements with which is essentially a gauge degree of freedom. But up to that, it's unique. And here phi is the golden mean. Okay. So that's the Pentagon equation. Then the remarkable another remarkable fact is once you've solved the Pentagon equation and made it consistent, you're done. If you consider 5 particles, 6 particles, 7 particles, you can do any sort of basis change, and you'll always get the consistent results. There will always be, in general, there will be many different ways to make the basis change, and however you do it, you'll always get the same result. So it's sort of in this exercise of building up a universe, starting with 1 particle, we had, yes, go ahead.
So is this the ability to get a unique F property of just the Fibonacci anyons? Or?
No, okay, that's a good question. And so of course, there's an infinite number of possible theories of non-abelian anyons. And generically, there is either, if not a unique solution, a finite number of solutions. So this rigidity is present in all of these theories. Yes. So anyway, introducing a particle, we had to introduce the notion of charge. Pairs of particles, the notion of fusion rules. 3 particles, the notion of the F matrix. 4 particles gave us the pentagon that fixed the F matrix. And then we're done. 5 particles, 6 particles, 7 particles, whatever set of basis changes you do can always be reduced to sequences of pentagons if you have different paths for doing the same basis change. And if the pentagon is satisfied, everything is fine. So I'm not going to prove that, but it's the easiest way to see that is just do some just play around with it a little bit and try to imagine doing basis changes. You'll see everything reduces to these pentagons. Okay. So we have a well-defined Hilbert space, and now's a good time to actually count the dimensionality of this Hilbert space. And to do that, let's consider some number of these Fibonacci anyons and imagine combining their charge in the way I've shown here. Yes. Oh, I'm sorry.
So can you say that for any fusion rule, I can always have a unique solution of F matrix?
No, that's not true. There exist many choices of fusion rules for which there's no solution. So for example, if I allowed for not just one version of a charge 1 object, but 2 versions, then there's no solution to the Pentagon equation. So at least from my point of view, if you write down fusion rules, it's not a foregone conclusion by any means that you'll find that you have a consistent anyon theory. Agree, so it's not well defined.
What you're saying is it's not consistent, it's just not a well-defined Hilbert space.
I guess I could do, I guess you could still have if I choose a particular labeling or set of ovals, as I've done here, where I label these, again, consistent with the fusion rules, I guess that's a perfectly good Hilbert space. But I'd like to be able to, I don't want to have the Hilbert space depend on how so here's the statement. I don't want the Hilbert space to depend on how I choose to combine charges. If I give you a collection of spin 1/2 particles, you're free to choose, okay, I'm going to combine these 2 spins first and these 2 spins first, and so on and so on. You can change from one basis to another using the Wigner 6J symbol, which is really what the F matrix is. The F matrix is a generalization of the Wigner 6J symbol. I guess there is a Hilbert space. If I choose a particular basis, there's a Hilbert space, but I don't want my Hilbert, so here's the statement. I don't want my Hilbert space to depend on my personal choice of basis. And for that to be true, the pentagon has to be satisfied. Okay. So with that, let's count the dimensionality of this Hilbert space. And a useful way to do that is to introduce this diagram here, known as a Bertelli diagram, where on the x-axis I have the number of particles, and on the y-axis I have their total charge. And the idea here is the paths correspond to different acceptable ways of labeling the charges here. So for example, the first one Fibonacci anyon certainly has charge 1. If I add a second Fibonacci anyon, it can have either charge 1 or charge 0. If it has charge 0, if I add a third one, it has to go back to charge 1. But if it had charge 1, it could be either charge 0 or charge 1, and so on. So states where, so here's a particular labeling of these ovals. 0, if the charge here is 0, the next one has to be 1, because if I combine a single Fibonacci anyon with topological charge 1 with something with charge 0, I have to get 1. This could be either 1 or 0. It happens to be 1 for this state. This happens to be 0. Then this has to come back to 1. And this corresponds to this path I've shown here. 1, so the first Fibonacci anyon, 2, 0, 1, 1, 0, 1. And here's another one just to hammer it home. The first two Fibonacci anyons have charge 1. If I add the third one, it comes down to 0, then back to 1, 1, and 0. And the usefulness of this diagram is I can determine the dimensionality of the Hilbert space just by counting paths in it. So, for example, if I can count the number of paths to this point right here, there's only one way to get from the origin to here. That just tells me if I have a single Fibonacci anyon, there's just one state. If I have 2, there's only one path to reach this point here with total topological charge 0. And there's only one path to reach this point here with total topological charge 1. Likewise here, if I add a third particle, there's only one path, this path here, to have, if the total topological charge of the first two is 1, there's only one path to come down to 0. But here, there are 2 paths. And the reason I can see that is because all I have to do is add up these 2 numbers here. There's one path to go here, one path to go here. They both connect to this point here. So basically, you just have to go back along these lines and sum the number of paths to reach the previous nodes. And here I get 2. So then, this is going to be 2. What's this going to be here? 3. And this down here? 3. There's only one way to go, but here? 5. 5 here. All right, so this 8, and then here I'll stop, but it's 13. Okay, anyway, you get the picture. Right? This is a familiar sequence of numbers. This is the Fibonacci sequence. And so it's a consequence of the fusion rules that the dimensionality grows as the Fibonacci sequence. That's why they're called Fibonacci anyons. And of course, the Fibonacci sequence grows asymptotically as the golden mean to the nth power. So it's an exponentially big Hilbert space, which is, from the point of view of quantum computing, is good because that's what you need to actually store your qubits and carry out your computation. Okay, so that's the Hilbert space. Now we need to manipulate it by braiding the particle. So we need to develop a little bit more of the mathematical structure of this anyon theory. So I'll remind you, so now I think I haven't said anything about dimensionality at this point, up to this point in our universe construction, but now I'm going to commit myself to a two-dimensional universe. It turns out I have no choice. I have to. And then this important feature of 2 + 1 dimensions that clockwise exchanges and counterclockwise exchanges are distinguishable, and exchanging is not its own inverse is crucial. Okay, so back to our universe and our anyons. What's the effect of exchanging them? Well, if they have a given total topological charge, A could be either 0 or 1 here. If I have 2 anyons, so one thing I don't expect to have happen is when I interchange them to have the topological charge change. This charge is something that shouldn't depend on any braiding I do within one of these ovals. So the most that can happen is I'll pick up some phase, and this phase will depend on the total charge. You can think of this as a generalization of a very familiar fact with ordinary spin. If you have 2 spin 1/2 particles, if they're in a singlet state, if you interchange them, you get a minus sign. If they're in a triplet state, you get a plus sign. So spin 0, you get minus. Spin 1, you get plus. Those, of course, square to 1 because 2 exchanges are equivalent to the identity. But for these non-abelian particles, that's not true, and we should expect these R phases to be complex. So for a clockwise exchange, you pick up the phase of R. For counterclockwise, it would be the complex conjugate of R. And so we can summarize the R matrix, or the values of R in this matrix here. They're just two. For Fibonacci anyons, we just have R0 and R1. And just as for the F matrix, let me make, I don't want to have to keep writing this, so I'll again use this arrow notation here, just to indicate what happens if I interchange particles and then I pick up some phase that depends on the total charge. So here, if I have three of them, if the total charge of these two is 1, the same reasoning I used for the F matrix, I can really think of this as a single Fibonacci anyon, and I can imagine exchanging these in this counterclockwise sense. Or sorry, that's clockwise, isn't it? In this clockwise sense. And it's equivalent to exchanging this blob of particles as a sort of coherent whole with this rightmost particle. So I can consider exchanges of more than two particles. I never have to use anything other than this R matrix. But an important point here is if this charge was 0, then I would just get 1. So of course, the phases are only important in as much as they're phase differences. So these phases, the phases of the R matrix, are measured against whatever the phase which we take to be 1 you get if you braid some object with charge 0, the same quantum number as the vacuum around anything, either with charge 1 or charge 0. Okay. So just as for the F matrix, there is a very strong self-consistency condition here. And we can see it by considering three particles. I've made them different colors so we can keep track of them as we move them around each other. And so let me imagine I have these three particles, and first I'm going to do a basis change, like so, using the F matrix, which we already know. That's already fixed by the Pentagon. Then I'm going to braid exchange these two particles with this in this clockwise sense. And then I'm going to do another basis change. So you can think of this is the sort of calculation you do if I were to imagine taking these two particles and braiding them around this third particle and then reading off the answer in this basis. But as for the Pentagon, there's another way to go. I could first have just interchanged these two particles, then performed a change of basis, and interchanged these two particles. I come back to the same state. In fact, this describes the same process. Here I'm braiding these two particles around this particle all at once. Here I'm doing it one at a time, but they're topologically equivalent braids. And so, again, I have to get the same answer regardless of which way I go around the hexagon. And so this is, of course, the hexagon equation, which is the partner to the Pentagon equation. And part 2 of the homework assignment is for you to solve the hexagon equation. So I won't spend as much time, but let me just do one quick run through of one can solve it essentially the same way you solve the Pentagon equation by choosing particular, all possible ways of labeling the state here and the state here. Again, you can think of this as I start with this state, I carry out this braiding process where I move these two particles around this particle, then I read off the answer in this basis. And I, in particular, read off the coefficient of this term. And so first I do this F move here. The total charge here has to be 1. So this is a test of your memory. Anyone know what coefficient, what should go here?
F0B.
F0B, exactly. Or let's call it A. So again, this is a non-trivial case. There are two possibilities here. So F0A, we're going to have to sum over both possibilities. Then going from here to here, this is also here I'm applying the R matrix, but here remember if A is equal to 0, we just get 1, because that's sort of by definition anything with charge 0 has trivial braiding properties. So if A is equal to 0, we get 1 because it's just the vacuum. If A is equal to 1, we're braiding one charge 1 object around another charge 1 object, and their total charge is 1. So we get R1. And then finally here, again, we get FA0. This is again a non-trivial case. Here, so now if I go down here, what term am I going to get here?
R0.
R0, okay. I'll stop asking these questions. And here, this could be either, it would be F0A, but this, we know that this has to be 0 because this is where I'm headed. So I pick up an F matrix element, but it's F00. I don't have to sum anything here. And then from here to here, I get another factor of R0 because I'm interchanging these two factors. So along the top path, I have to sum over these two possibilities here. And the bottom path, I get this term. So we get an equation. Now, we already know F. You solve for F. So the only unknowns here are R1 and R0. I believe if you work out all the non-trivial allowed cases, there are 4 cases. I've done one of them, so you have 3 more left to do. So you'll have 4 equations. And again, if you use the unitary F matrix you found from solving the Pentagon, you'll find there are 2 and only 2 solutions for the R matrix. And these are the solutions right here. If you think about it, there had better be 2 because we haven't really specified the handedness yet. I mean, if we find a solution R, there better be a solution R star, corresponding to replacing all clockwise exchanges with counterclockwise exchanges. So a particular, this, of course, in the context of the quantum Hall effect, it depends on the direction of the magnetic field. Yes?
Sorry, just to make sure, are these 2 paths correspond to one group, element of Braid's group? I mean, one element, are it just same element of Braid's group? I mean, it's not clear here because you're exchanging 2 things.
Yes, I mean, yeah, here, I mean, well, let's see, I'm not sure.
Should they be the same?
I think they're topologically equivalent. They better be.
Yeah.
So, so here I'm sort of braiding these 2 in one go around the third one. And if I go the other way, I first interchange these 2, and oops, I make sure I do it in the same sense, and then I interchange these 2. And so these, I think these are clearly topologically equivalent. Here, I move this particle around this particle, and then I move this particle around this particle. So I braid this around this, then this around this.
But I mean, for example, for the first one, the first element goes to the third one.
Oh, you're right. That is an equivalent. So yes. So what? Oh, let's see. That's embarrassing. Let me make sure I have this right.
I think you need one more element there. Then exchange third and second and third element in the first diagram.
The second in the first diagram. Let's see. Let me make sure I.
You
So
have 2 exchanges.
let me just see the colored picture should make it clear. So I'll spend this. So here I've moved the green and red particles, or oh yeah, I did. So I did this wrong, didn't I? This picture is wrong. It's actually, because the first thing is the basis change, and then so I think I'm still okay. Right? The first exchange is actually so of course I mean so it's 1 2 3 1 2 3 so left to right here is bottom to top, and so it's really these 2 I'm braiding around here, and I think that's equivalent to this. Can I breathe a sigh of relief? Okay. All right, so we have our equation. And yes, these correspond to two distinct ways of calculating the topologically equivalent braid. If not, you can include that in the homework solution. And unique solution. Okay, and just like for the Pentagon, I'll state without proof that once you've satisfied the hexagon, everything is fine. So you can we now don't just have a well-defined Hilbert space that doesn't care how I choose to label the basis states. It also doesn't care how I choose to calculate the effect of braiding the particles. Whatever sequence of braiding operations and F matrix operations I apply, I will get the same answer because of the coherence due to these self-consistency conditions. And so one of the things that comes out of this, just very quickly, is, let me just summarizing everything. This is really the basic content of any anyon theory. There's always some set of charges, fusion rules, an F matrix, an R matrix, a Pentagon and Hexagon. They're always there for Majorana fermions, for whatever your favorite non-abelian particles are. And even for ordinary spin, the F matrix is the Wigner 6J symbol. The R matrix encodes the -1 or +1 you get for interchanging spins if they're in a singlet or triplet. And one of the things you get out of this is essentially a matrix representation of the braid group. Just very, the braid group, of course, is a mathematical group that consists of the elements are braids, where braids are strands which are stretching from all going in one direction, or can be stretched so they're all going in one direction. So here are elements of braids. And an example of something that's not a braid because I can't stretch it to make something like this would be sort of drawn there. And it's a group because there's the rule for group multiplication is you just sew the braids together. And then in this case I can, since this is, I can undo this. This is topological equivalent to this. And we can generate the braid group by elementary operations. So any braid can be built out of elementary operations in which I'm just interchanging neighboring pairs of strands, or braiding neighboring pairs of strands. So for example, sigma 1 would be braid strand 1 over strand 2, sigma 2, 2 over 3, sigma 3, 3 over 4, and so on. And so any braid you write down can be expressed as a product of either these elementary braid operations or their inverses. This is sigma 1 inverse because here the top strand is going above the bottom strand. Now, of course, there are many. If I hand you a braid, there are many different ways you could sort of lay it down on the ground and express it in terms of elementary braid operations, all of which are topologically equivalent. And this equivalence is encoded in the braid relations here. The sigmas satisfy these algebraic relations, and this essentially, given these relations here, that's all it takes to. As long as the sigma satisfies these relations, then it's guaranteed that however you calculate the effect of braiding, it will only depend on the topology of the braid and not the details of how you actually sort of lay, if I tangle it up in some complicated way, you'll always get the same answer. And so from our Fibonacci anyon theory, we can, for example, work out the braid matrix representation of the braid group on 3 strands. And so I said I wasn't going to ask any more questions, but let me ask a question. So here I have, let's consider 3 particles. Let me simplify things and say, let's fix the total charge to be 1. This charge A can be either 0 or 1 now. So I have a 2-dimensional Hilbert space here. If I interchange these bottom 2 particles, I'll perform some matrix operation on the Hilbert space. So what is that matrix operation? R, brilliant. It's just R. If A is equal to 0, we get e to the minus I4 pi over 5. If it's 1, we get e to the I3 pi over 5. I made a particular choice, one of the choice of those 2 possible R values there. what about here? How would I calculate the Braid matrix here?
This is F and then
Exactly. I mean, we have all the tools we need. First, I'll apply F to change basis. Then I'll braid these particles. That'll be R. And then I can do F inverse. F is its own inverse, so I'll just write F instead of F dagger. Doesn't matter. So sigma 2 is the matrix product FRF, which it's not terribly important. It has this form here. Tau is the inverse of the golden mean. And again, what these matrices give us is what it allows us to do is to calculate the effect of braiding these particles. So if you hand me this braid, I just can divide it, break it into elementary braid operations. And it doesn't matter how I do that, as long as the braid is topologically equivalent. When I take the product of the corresponding matrices, or their inverses, I can calculate the unitary transformation that this braiding process carries out on this Hilbert space. And you'll always get the same answer for topologically equivalent braids. Okay. So, and it turns out this is all I'm going to need I only need the matrix representation for three-stranded braids. Because what I want to do now is in this universe we've created, I want to actually build a quantum computer. And so one reason for doing that is just to show that I want to sort of demonstrate the statement I made that the braiding of Fibonacci anyons is universal for quantum computation. And one way to do that is just to show we can create qubits and we can carry out arbitrary quantum computations with those qubits. It also has the quote-unquote practical benefit that most of the interesting quantum algorithms we know, like Shor's algorithm, are expressed in terms of sort of the standard language of quantum computers, with qubits and quantum gates, controlled NOT gates, things like that. Whereas the natural language of Fibonacci anyons, or anyons in general, are these braids. And we have to somehow be able to translate between the two. Okay, so, yes? Oh, it could be R. It should have been R. Sigma 1 happens to be R.
Okay.
Yeah, sorry, I should have put R there. I apologize, yeah. But it's the same thing. Oh. So the first thing we have to do if we want to build a quantum computer, a conventional quantum computer, is we need qubits, and one issue that comes up here is the Hilbert space for Fibonacci anyons doesn't have any sort of natural tensor product structure. It's this beautiful Fibonacci Hilbert space. So one is forced to sort of do some violence to that Hilbert space and force it to have a qubit structure. And one can do that by encoding. And this is a theme in many quantum computing schemes, not just with non-abelian anyons. And here, for example, the simplest encoding scheme is one where we use 3 anyons, fix their total topological charge to be 1, and as we've seen many times now, that's a 2-dimensional Hilbert space. I'll make a basis choice and say that the charge of these 2 leftmost particles tells me the state of the qubit, either 0 or 1. And so that's our qubit, but the price we pay for this encoding is there exists some state, a non-computational state, the state with topological charge 0. And we have to work very hard to make sure we don't induce transitions into this non-computational state. Those are leakage errors. Yes?
Why don't you just use that state too? Like 0, 1, 2. Is it so bad?
Use the state.
Like you make superpositions of all 3.
You could, but you'll see. I mean, first of all, one doesn't have as much freedom to carry out arbitrary. The nice thing about this is, well, is I can carry out arbitrary single qubit operations here, whereas I can't, if I'm braiding within these three particles, I can't induce any transitions from here to here. So if I wanted to use this state, I'd want to be able to induce transitions to it. Now, if I have, so you could do that, but I think it adds more complications than, as I say, if your goal is to do something like carry out Shor's algorithm, and you know how to do Shor's algorithm using qubits and quantum gates, then this is. This really is the simplest procedure. You could keep this qubit, but I wouldn't know what to do with it. Maybe, but so for the moment, let me just set as an exercise for myself. I want to build an ordinary quantum computer with qubits. And just a quick aside about how one in this one can at least envision, fantasize about initializing the qubits in the context of the quantum Hall effect. Say, if the 12th state is indeed a Reed-Mazai state, you can imagine pulling quasi-particle, quasi-hole pairs out of the vacuum. Something I didn't tell you is that quasi-particles and quasi-holes are both Fibonacci anyons. So they're equally valid. We can use them for this non-abelian quantum computation. We can use mixtures of them. And if we pull them out of the vacuum, the total topological charge is 0. And likewise, if I pull another pair out of the vacuum, the total topological charge is 0. And then from the fusion rules, well, I know the total topological charge of all four is 0, but the total topological charge of these three then has to be 1. So right there, I've through this procedure, which admittedly would be very hard to carry out experimentally, I've initialized a qubit. And then at the end of the day, we carry out our computation. We want to measure our qubits. So maybe it's in some particular state, alpha 0 plus beta 1. And what we can do is try to bring the quasi-particle and quasi-hole back together again and see if they fuse back into the vacuum. If they do, we know they had the same topological charge as the vacuum, 0. If they can't, if they don't, if they can't fuse back, then the topological charge is 1. So I don't propose this as a serious way to actually do this necessarily, but really just to give you, it's an existence proof that one can at least envision ways to initialize these qubits and measure. So we have a qubit. We have a two-level system. And like any two-level system, I can represent the pure states by points on the block sphere. And I can represent single qubit operations as rotations with some rotation vector alpha, the magnitude of which is the rotation angle, the direction is the rotation axis. And here, so this corresponds to some single qubit operation, U alpha here. This is this quantum circuit notation, which people are probably familiar with. This line represents a qubit, and this is the unitary operation we carry out on the qubit. And so the set of single qubit operations lives in a sphere of radius 2 pi. So these are all the possible rotation vectors and rotation axes. And of course, from the point of view of ordinary quantum computing, this is a source of potential error, because if you have say a spin qubit and you want to rotate it by applying a magnetic field, you better apply the magnetic field in as close to the right direction as you can possibly get, and for just the right amount of time, and you're never going to get it exactly right. There's always going to be some error. So this reflects this, again, sensitivity of qubits to error. But now what I want to ask is, with our topological qubit, as we braid the particles around each other, can we carry out arbitrary single qubit operations? And it's actually, that's a pretty trivial, straightforward question, since we have two elementary braid operations and the corresponding matrix operations. So the real question is, do those braid matrices correspond to rotations for this qubit? Do those rotations generate a finite subgroup of the rotation group or not? So here are the rotation axes corresponding to the braid matrices we've derived. and actually it's not just braids, let me call this a weaving pattern where I take this particle and I weave it around the bottom. So it's a product of, this is sigma 1 squared. And here's sigma 1 inverse squared, and sigma 2 squared, and sigma 2 inverse squared. So these are elementary weaving operations, because if I keep doing these over and over again, I can really think of it as just weaving the blue particle around the green particles. And so if you work out the rotation axes, this is what you get. It's not, so if I could only rotate about a single axis, because remember this phase factor is e to the I 3 pi over 5. If I rotate 10 times, I'm back to the same state. So I can't generate arbitrary rotations about a single axis. But of course, I have two axes. And so let me remove I'll just remove the axes and just leave the points at the end of these rotation axes. So these are the 4 possible rotations you can carry out with the 4 possible weaving operations where I do just a single weave, which consists of 2 elementary braid operations. This is just a representative. There are 4 of them. So if I do the next one, there are going to be 16. Again, here's a representative braid. There are 16 distinct braids. And so on and so on. And it grows exponentially. And again, this shouldn't be so surprising. This would be the generic case if I have 2 rotation axes and 2 fixed rotation angles. The generic case is that those rotations do not generate a finite subgroup of the rotation group corresponding to some Platonic solid. And indeed, the Fibonacci anyon case, they make some weird angle, which is the arctangent of the golden mean or something, is certainly a case where is the generic case where we can carry out any arbitrary rotation. Now, from a practical point of view, if you have your quantum computer, how are you going to? There's a particular single qubit operation you need to perform. How are you going to find that? Well, the first thing you would consider is just doing a brute force search. Say I want to do a rotation that corresponds to some point here. I just search braids. And so, for example, here is an example of searching for a particular braid that carries out this operation here, which is a not operation. It flips 0 to 1 and 1 to 0. It's a factor of I. It doesn't matter. And so you can do that. You can do much better than that. This is you can get out to about here without much difficulty. Probably around here is the lifetime of the universe. I don't know, but because it's exponential, right? The number of braids is growing exponentially. So in this case, the accuracy is about 10 to the minus 3. That means the matrix elements that don't correspond to the matrix I want are on the order of 10 to the minus 3. And as you might expect, since once you start letting these braids get longer and longer, you're basically randomly, more or less, filling in this sphere, and with an exponentially growing number of points. So you would expect that the length of the braid would grow logarithmically with this error. And indeed, this is just from numerics. But from the point of view of quantum computing, that's not good enough, because if you want to carry out things like Shor's algorithm, you have to be able to carry out rotations or quantum gates to whatever I don't want to say arbitrary accuracy. The accuracy with which you have to carry out each quantum gate is dictated by how large the problem you want to solve is. Let's say if you're carrying out a billion gates, you have to make sure that each gate is accurate enough that the errors associated with each of those billion gates don't add up to some significant error. It's okay to have, in fact, you always only have a finite probability to get the right answer, but in a quantum computer that's okay, because you can always check, if you're factoring some integer, you can always check multiply the two numbers together to get the original integer. If not, run it again. But as the number of gates you have to carry out gets bigger and bigger, as you scale the size of the problem, the accuracy of each of those gates has to get better and better, and there can be no limit to that. So it's not enough to be able to just go out to 10 to the minus 3. You have to be able to, in principle, go out to make this as accurate as needed. Now, fortunately, so as I say, brute force search is, rapidly becomes infeasible for that. But fortunately, there's a very clever algorithm due to Solovey and Kitaev, which allows one to systematically improve these braids. Given a sufficiently dense covering of SU2, as I just showed you, once you have a dense enough library of braids, then what the Solovey-Kitaev algorithm tells you how to do is how to take these braids and sew them together in a clever way, so that you can improve the accuracy systematically, without having to do a deeper brute force search. You can just live within that library. So, for example, this is one iteration of the Solovey-Kitaev algorithm for this braid here. The accuracy goes to 10 to the minus 5, but in fact, one can show it asymptotically. The braid length grows polylogarithmically with the error, so it's not as good as brute force search. This exponent is about 4. So I should, as a heads up, I should point out there has been a recent breakthrough in this area. You can read about it in this PRL. A new, very clever method, which amazingly enough seems to only work for Fibonacci anyons, at least so far, allows one to actually improve the scaling so that the braid length grows as log epsilon. But polylogarithmic is good enough from the point of view of quantum computing. So the braids are going to get, as the problem you want to solve gets bigger and bigger, the braid length is going to get bigger and bigger, but only logarithmic. Okay. So we have part of our dictionary for quantum computing. If you give me a single qubit operation you want to carry out, we can find a braid that will do that. But of course, it's not enough to do single qubit rotations to do quantum computation. You have to entangle qubits with each other. You have to be able to do 2-qubit gates. And one particular class of 2-qubit gates are so-called controlled 2-qubit gates. That means you have a control qubit, and in this case the top qubit. And what this means, and if the control qubit is in the state 0, you do nothing to the state psi, or the state of the target qubit, the bottom qubit. So it's unchanged. Whereas if the control qubit is in the state 1, you carry out some operation U on that state. And the most famous example of this, of course, is I'll use this X stands for sigma X, the Pauli matrix. It's a NOT operation. This is the controlled NOT gate. So it flips the state of the bottom qubit only if the top qubit is in state 1. Otherwise, it does nothing. And this is a standard choice for so-called universal set of quantum gates, single qubit rotations and controlled NOT gates. That's why everyone who comes and gives a talk about their scheme for building a quantum computer always has to tell you how they're going to be doing their single qubit rotations and how they're going to be doing their controlled NOT gates. And the fact that makes these universal is that any unitary operation can be expressed as a quantum circuit built out of single qubit rotations and controlled NOT gates. So in some sense, the question I've been assigning myself is, okay, what is the braid that corresponds? I should be able to translate any quantum circuit into a braid of Fibonacci anyons. And so far we can do the single qubit rotations. What about the controlled NOT gates or 2-qubit gates? So that's a much harder problem because for two reasons. One reason is once we start trying to braid anyons from different qubits with each other, we have to pull anyons out of their encoded qubit. So remember, one of the nice things about single qubit rotations is as long as we were braiding within one of these ovals with well-defined topological charge 1, that topological charge wouldn't change. So we had none of these leakage errors out of the qubit space to this non-computational state. But as soon as you pull an anyon out of its qubit, then in general you're going to induce transitions which will change the charge of the qubit and lead to leakage errors out of the computational space. So that's problem one. Problem two, the much worse problem, I would say, is just the size of the search space here is enormous. it's essentially it's SU5 plus SU8. Because there are 2 seconds. The total topological charge of all 6 of these particles can be 0 or 1. And the set of unitary operations, it's a 5-dimensional Hilbert space and an 8-dimensional Hilbert space if the total charge is 0 or 1. 5 and 8 are 2 Fibonacci numbers. But I'm searching on the space of unitary operations acting on that space. And so the analog of the 3-dimensional sphere, which I can use to search for just single qubit rotations, becomes an 87-dimensional space. And that really becomes totally infeasible. So we have to make our life easier. So first, let's focus on the controlled qubits, controlled 2-qubit gates I was telling you about. So not a particular class, a useful class of 2-qubit gates. So I have a control qubit and a target qubit, and I want to find some braiding pattern where I carry out an operation on the target qubit if and only if the control qubit is in the state 1. If the control qubit is in state 0, I want it to do nothing. So I don't know, this is not a fair question, but does anyone have any idea how we might do that? So I'll remind you one of the properties of these particles is if I have something with charge 0 and I braid it around anything, it does nothing. It just carries, you just get the identity operation because it has the same quantum numbers as the vacuum. Only objects with charge 1, if I braid them through around other anyons, will induce transitions. So
around the loop.
exactly. Though rather than let me bring the mountain to Muhammad rather than whatever the reverse of what you did, but the same idea. Let me or bring Muhammad to the mountain. I don't know. Let me consider only those braids where I take this pair and I weave it around this. This is equivalent to what you said. You wanted to keep this fixed and braid everything around these guys here, but it's the same thing. And built into this is whatever we get, it's going to be a controlled something. Because if the control qubit is in the state 0, this pair of particles, which we call the control pair, will have charge 0. And it will do nothing. It only has a non-trivial effect if the charge is 1. So, and if the charge is 1, for simplicity, let me replace the pair by a single Fibonacci anyon. The case when b is equal to 0 it takes care of itself. We know it's going to do nothing. So let's just focus on the case when the charge is 1. And so now I've made things simpler. Instead of braiding 6 objects, I'm really only braiding 4 objects. I'm braiding the control pair through the target. But even this is too difficult, it turns out. Yes?
But do you really need a controlled arbitrary rotation? Isn't it enough to just have controlled knot?
It's enough to just have controlled knot. In fact, it's enough to have controlled anything.
And you don't need to search for it in the 87-dimensional space, right?
True.
Well, you need to search for it once.
True. But there is this crucial issue of the leakage. In other words, at this point, it's still the problem here is, as I weave this through, I'll do a controlled something, but in general, I'm going to induce some transition in this qubit out of the qubit space. I'll induce a transition from 1 to 0. So that's one problem. Another problem is a feature of this is that we can never get exactly what we want. We can only get, just like in the single qubit rotations, we can only get asymptotically close to where we want to go. So I can't do a single search. I have to be able to improve things systematically. But I take your point. You're saying rather than choose a particular gate and search this whole space, you can search this space for a smaller subspace that consists of entangling 2-qubit gates. You can do that. That does simplify things, but it still doesn't simplify things enough to make it feasible. Yeah.
That's this guy around the entire block. Isn't that a controlled phase gate?
You want to wrap this guy. You want to wrap this guy all the way around.
And then back. Because
Well-
that's one wrapping around one equals the other.
Well, this one, it's not a controlled phase gate because for a controlled phase gate, you have to give a phase. You have to give a -1 to the state where both qubits are in the state 1, and otherwise do nothing. So essentially, I mean, what you're proposing doing is bringing this all the way around, and this gives a phase of some phase if this qubit is in the state 1, and no phase if this qubit is in state 0. That amounts to doing a single qubit rotation here. So that's a way to do a single qubit rotation on the top qubit. So that it's a good idea, but it doesn't work. So let's make our life even easier, and simplify things and bring things to a level where we know we can handle it. We know that we have 3 braids, braiding 3 strands well in hand. Let's just weave the control pair around the top 2. So then, so this again, it's guaranteed to do a controlled something, and I don't care what it is, because any controlled anything is good enough. I really mainly care about leakage. So the trick is to find some weaving pattern that doesn't induce a transition out of the encoded qubit space here. And I could write down some of the mathematical equations that requirement forces you to satisfy, but it's easier to just show you the answer in pictures. The answer is, what you can do is, and this is in fact the unique answer to this, you find some weaving pattern where I'm weaving this particle around, let's say the top 2 particles there. I find some weaving pattern which approximates the effect of braiding these 2 green particles around each other. If you like, it's sort of like the blue particle is like a magic wand. You just wave it. The green particles stay still. You wave it around in this pattern, and the unitary operation it carries out is the same as just braiding the bottom 2 particles. And the reason why that is a useful thing is because if I put that here, if I follow this pattern, so again, this is just the result of a brute force search to find something that approximates this operation here.
What is that approximation here?
Sorry?
So why is it not exact?
So one question is, can I prove that there doesn't exist an exact solution to this? I'm not sure I can, but it is a fact that you cannot. You can only. It's just like if you give me some arbitrary single qubit rotation, or just you tell me you want a NOT gate, just like the example I gave. There is no finite braid that produces a NOT gate. As it happens, it's actually true. I've thought about it. I don't know how to prove that there doesn't exist some finite braid that does this. I don't believe there is, and certainly all of our numerical evidence suggests there isn't. It would be very strange if there was. But you can just think of this. We're doing, this sigma 1 squared corresponds to some point in the sphere of rotations I showed you. And the question is, does that point correspond to another point that corresponds to a finite braid where I'm, instead of braiding these 2 particles, I'm braiding this blue particle? The answer, I'm 99.9% certain is there is no finite braid that does it. It is true, I don't know how to prove it.
Can you find fusion rules that will give you an F matrix that will naturally give you some right angle rotations to make NOT gates or something?
You can. Those are, in fact, those are so it's a mixed blessing. Those are the braiding properties of Byronic fermions, which we'll be hearing about soon. By the way, how am I doing on time? I forget when do I end? So is it now? I can't tell. I can't tell. I honestly have lost track. Oh, 3 more minutes. Okay. So for Majorana fermions, indeed, the rotations in the sphere correspond to 90-degree rotations about perpendicular axes, which is perfect for making NOT gates, and also even controlled NOT gates. But it's bad from the point of view of universality because, yes, you can do that, but you can't do arbitrary single qubit rotations. If I can only do 90-degree rotations about this axis and this axis, then that's the case. That's a simple case that corresponds to generating a finite subgroup of the rotation group. So you can't carry out single qubit rotation. So this is this famous fact, which I think I'll have something to say about next time, that minor nanofermions they have all of this in principle, have topological protection, and you can do some gates by braiding, but you can't do everything by braiding. So you will always have to, for any quantum computation scheme that uses minor nanofermions, you will always have to supplement the braiding with some non-topological operation. So let me, in the remaining 1 minute, let me just finish this story here. This will be, then I'll have a good starting point for the next time. So again, so once you've found this weaving pattern that generates this effective braiding, if I use this pattern here, you can see what happens. This is the control qubit. If the control qubit is in state 0, it does nothing. If the control qubit is in the state 1, this weaving pattern is equivalent to just braiding these two green particles here. And remember the rule, if I'm braiding within a qubit, I don't induce any leakage error. And so in fact, we get what as we jokingly call a controlled NOT gate. But this does suffer from this problem that it's only approximate, and just like arbitrary single qubit rotations, we have to use Solovay-Kitaev to improve it. So this is, for example, 1 round of Solovay-Kitaev on this gate. Okay, so I am not sure about the time. Is it? Sorry? 1 more minute doesn't count. I'll ask for, I'm thinking, do I have enough time to start a new subject?
Maybe not.
Okay, so I think this is a good place to stop for today. Maybe see if there are any questions, more questions. Yeah.
So you say you can initialize a 0 or 1 by having fuzzy particles pop out of that vacuum and just group them. How could you then get into a superposition?
Well, then I'd pull a pair out here, pull a pair out here, then I'd braid one from one pair, one from the other pair.
Single quasi-particle.
Single quasi-particle, yeah. So I could if I pull a pair out here, then I braid these two, then I perform some unitary operation, and it's no longer, then there's going to be some probability if I bring these two together that they fuse to 0 or they fuse to 1.
It's not one of the logical gates that you were talking about. It's some other unitary that puts it into the superposition.
Or you could, once you initialize a qubit in the state 0, then as I just showed you, you tell me whatever state you want. I can find a unitary operation that produces that state and find a braid that produces that, and you just braid them.
It wasn't clear why the controlled phase that somebody suggested behind me wasn't quite right. Like you just take those 2 and then braid them all the way around the other 3.
I think the reason that would not lead to any entangling gate. That's really equivalent to a single qubit rotation, because essentially what you need to have happen is you have a control qubit and a target qubit. You need to have something happen to the target qubit if and only if the control qubit is in state 1. Now the gate that was described is one that would just gives the whole state. Multiplies the whole state regardless of the state of the target qubit, a phase factor if the control qubit is in state 1. So it's really so in other words, if I start with a tensor product of a pure state for the control qubit and the target qubit and carry out this gate, I end up with again a tensor product. It leads to no entanglement. It's a single qubit rotation. So there's no, what you have to do is you have to induce some sort of transition in the target qubit, perform some rotation on the target qubit if and only if the control qubit is in state 1. And this procedure doesn't do that. It's really equivalent to just doing a single qubit rotation on the control qubit.
Is it surprising that you have this control qubit which can act like a magic wand and induce an arbitrary unitary transformation on the other 2 qubits?
I think, no, not really, because what I tried to show you before is you can do arbitrary single qubit operations. You can get arbitrarily close to whatever single qubit operation you want to achieve, and this is just one example of that.
Yes,
so,
but those arbitrary single qubit operations were combinations of 2 different kinds of rotations. They were.
Well, that's still true here. I have. I have 3 anyons, and I can braid them on carrying out unitary operations that correspond to the elementary operations are the same rotations I showed you before. And so it isn't surprising because what we know is you can get anything. And so it just happens that the only things that for which you'll get no leakage are these effective braiding weaves.
So eventually you map your ionic system onto some kind of rotations on Bonesteel. So why a spin cannot do that basically? Simple spin qubit.
A simple spin qubit can do that.
Yeah, so in the sense that what is this?
What's the advantage of this?
Yeah.
So the advantage is the topological protection. There are 2 advantages. One is unlike the ordinary spin, for the ordinary spin you have this local spin degree of freedom which suffers decoherence from, say, nuclear spins or whatever. Whereas here we have a topological qubit built out of these anyons, which if they're well separated, you keep the anyons far enough apart, the states of the qubit are topologically protected. So presumably have maybe not an infinite lifetime, but a long coherence time. That's advantage 1, is built-in protection from decoherence. Advantage 2 is, for the spin qubit, yes, I can perform arbitrary rotations by, say, applying a magnetic field, but I'm never going to get it exactly right. I'm always going to produce errors. That's not death to quantum computing because you can use quantum error correction. But here, the operation depends just on the topology of the braid. So as you braid the particles around each other, you don't have to carry it out perfectly. You don't have to carry out or regardless of how you carry out the braiding process, as long as it's topologically equivalent to a braid that produces the operation you want, you'll get the operation you want. So there are 2 benefits. One is the topological protection. The other is the topological braiding, robustness of braiding.
But there should be some trade-off between what you can do with a spin qubit, and seems like there are a lot of practical constraints to realizing this.
Yes, I mean,
What is the trade-off in both these cases? Is the protection really worth that much?
Where I think this is heading, and is that these ideas of topological protection and topological order and topological quantum computation are sort of being absorbed by the mainstream quantum computing community using spin qubits or superconducting qubits or trapped ions, your favorite qubit. Where the philosophy there is you're quite right. I don't think this is ever going to be done. I should have made that clear. This is right now this is just a sort of thought experiment or a question about what is at least the potential properties of these states of matter. But if you have a quantum computer, what you can do is actually create these states, if you like. So this so-called surface code, which is I think probably the most promising proposal for doing quantum computing, is based on realizing the ground states of the Kitaev toric code on an array of qubits, not with a Hamiltonian, like the Kitaev Hamiltonian, but use the quantum computer to measure the vertex and plaquette operators, and then you have anyons. There are abelian anyons, but it turns out you can still do quantum computation. I'm not proposing this as this particular scheme. Although at the same time, I don't want to be so foolish as to completely rule it out. Who knows? A few breakthroughs and this sort of thing might actually be feasible. But I really think this is more just we're learning something about these states of matter and in fact something that I think that I hopefully will have time to talk about in the next lecture is the idea of realizing these Fibonacci anyons in this surface code sense with a quantum computer. And quantum computers with 10 or 12 qubits with long coherence times and accurate gates, they're coming. I think one of the things people are going to be doing with them is creating these states. And so one can envision, I actually think long before this is done with a 12/5 state, it will be done. But you'll create Fibonacci anyons on a quantum computer and braid them around each other. And there it's a scheme for quantum error correction. So I think that's my best answer to you. I mean, I think in the end, the spin qubits will be using ideas from topological quantum computing, building them into when you actually start trying to do quantum computation. Yeah, it's my best answer.
Okay, let's thank our speakers again. This lecture will start at 3.